Thank you for the introduction. I want to thank the organizers for the invitation. It's nice that we can finally be here. I'm happy to be here in Vienna. So just I will start with apologizing slightly because there is no stochastic PD. Oops, so what we're looking at is we're looking at an solution on path space, but it's not a PDE. And also, in fact, it's deterministic. But there is still some stochasticity because we will look at stochastic initial condition. Okay, so not a stochastic PDE, but also not so far from one. Okay, and what I will talk about, it's a joint work in progress with my PhD student in Dauphine. Okay, so the talk I will do in three parts. So first I will try to describe quickly, the problem that we are looking at, the control problem that we are looking at. Then I will explain why we were looking at this, where the motivation was coming from, and in fact it's a motivation from learning for deep neural networks. And finally, the main part of the talk, I will talk in more precise details about what are the mathematical results that we obtain. Okay, so let me start with describing the problem that we're looking at. So it's somehow very simple, very classical deterministic control. So we have, we start from a point X in Rn, and we want to move it to a point Y, and also in Rn. And the way in order to do that, we have a constraint that we can only move in D directions, which are given by V1. So we have D vector fields. And at each step, we can only move in some linear combination of these vector fields. And what we want to do here is doing something like this, find a way to go from X to Y. Okay, and of course, the interesting situation is when the number of directions at each point, D, is strictly smaller than the total, the ambient dimension n, okay, which means that at each point you can only move in a smaller dimension subspace, but nevertheless, there are some classical criterion that guarantees that you can still move from any point to another point, and this is this so-called Hörmander condition, which basically tells you to look at the Lie brackets. Because the Lie bracket basically tells you that by combining the vector fields in some way, you can in fact create more tangent directions, and this means that if these tangent directions do span the whole space, then you can actually have some kind of global controllability, where you can really go from any point X to any point Y in this small number of directions. Okay, and this, like I said, this is very classical. In fact, this theorem, which is called the Chow-Rashevskii theorem, it's very, it's from the 19th century. Okay, so we are going to always be in this setting where we assume that these vector fields they do satisfy this condition. Okay, I assume most of you have seen something like this before, but maybe just in case you have not, the simplest example of such things is when so-called Heisenberg group, where you have a two-dimensional control and an n-dimensional ambient space, which means that okay, you want to control three coordinates, but you can only go in two directions, which are given like this in the coordinates. And in fact, okay, maybe I can draw a small picture because this can be described in very simple geometric terms, which means that, okay, let's say you want to go from the point 0 to the point x, y, z, and in geometric terms, the interpretation is simply that you want to find a path that goes from 0 to x, y, so the first two coordinates are just this, and then the third coordinate means that you want to find, somehow the area in the path that you're going through, this should be z, or maybe 1/2 z. And of course, when you see this, it's immediately obvious to everyone that whatever the point and whatever the area, you can always find a path that does this. So yeah, this is an example of this, where you have a two-dimensional path. You go only in two directions somehow at each point, but you can still solve this three-dimensional. For this three-dimensional, sorry, these three coordinates, you can always find one point to the other. Okay, so this is like the simplest example of such situation. But of course, this criterion is very general, and you can do much more complicated. Okay, and now the question that occupies us is: we know these controls exist, and we would like to find them by a very not very clever method, okay, which is to do a gradient. Okay? And this means you can look at, okay, you want to that this is your endpoint, and you would like your endpoint to be y. So So you just see this as a function of your control, and let's say you take the norm squared for something which is nicely differentiable. Okay, and this is, you have this positive function L, and you want to find the zero of it. So of course, the natural thing to do is to draw a gradient flow. Okay, and for instance, here we had, I said, okay, this is maybe not so important. Let's say we wanted something in L2, so you have this gradient flow. You have, and your map here is smooth from L on L2, and you can do a gradient, so you can set up your gradient flow. And basically, the whole question that we are interested in this talk is, does this work? And when you do this, do you converge to a solution of the control? Okay, and the first thing that you do is you start to ask yourself some basic questions about this function L. For instance, if you want to find a minimum of a function by gradient flow, a very bad thing is that if you have local minima, which are not global minima, because of course in that case, this means if you start near this local minimum, you would not converge to the global minimum. And the good news is that in that case, this cannot happen because of this controllability condition. Whatever control you have, you can always change it just a little bit to get closer to the target. So there is no local minimum which is not a global minimum. However, I mean, okay, the next bad things would be saddle points or critical points. Okay, so point where the gradient is zero, but I mean, it's not a minimum, but still the gradient is zero, and it's not a global minimum. And in fact, the problem is that this exists. And one way to, I mean, it's very easy to see this because, I mean, you do the computation for the gradient of this thing, and I mean, just by the chain rule, it's just, let's say, the distance to the target against the gradient of the map, of the endpoint map, which will control gives you the endpoint. And in fact, yeah, you see that it's possible. I mean, okay, the bad thing would be that this is not zero, so you are not at the target, but somehow this scalar product is zero in the sense that there is no direction of the control which goes in this, I mean, or the directions in which you can go by changing the control here are all orthogonal to this. And somehow it's always possible to find something like this, as long as we are in this situation when the dimension of the control, I mean, the number of directions d is strictly smaller than the dimension n. And for instance, I mean, if you look at the control zero, it's always singular in this sense, okay? Because okay, if you have a control, if you are zero and you just take a perturbation of the control zeros, and at the first order, you can only move, in fact, in this d directions, v1 to vd, okay? And so if your target was somehow orthogonal to this, you in fact don't move, okay? So the gradient flow, it doesn't have local minima, but at least you can find examples of initial conditions that would not converge, that would get stuck without converging. And another serious problem when you are trying to analyze this, so sorry, there is a line that's missing here, but in terms of optimal control, this is a bit weird to look at this like this, because typically you add a cost, okay? So here there is no cost, which means that, okay, we are just looking, the only thing we are asking for you is that it's, I mean, we want this to be exactly equal to the target, so we don't add anything, but this also means that somehow there is no a priori bound from the gradient. This function L of u, it has some zeros. We know it has some zeros from the chart theorem. But it has also, but in fact, it has really a lot of zeros, and these zeros are not bounded a priori. So there is no there is no obvious reason why this stay bounded. Okay, so it's not clear that it converges, but also it could diverge to infinity. I mean, for instance, here you can, just from this picture, it's clear that you can find paths which have the same somehow area, but which are very, very irregular. So there is no a priori bound on the zeros of the function. So this term is not coercive. Okay. Right. Okay. So now the next thing. Okay. So like I said, I can find you some example of starting points which would not work, or you would get stuck immediately. But we can expect, I mean, if you think of a function, generic function, I don't know, saddle points will typically, you would not have so many of them, and okay, maybe if you take a point taken at random, then you would somehow you would not converge to them. So this is basically the hope that you take a random initial condition and then you converge. And one thing that is known, I mean, that goes back to the work of Malliavin, is that one thing that you use in Malliavin, that Malliavin used in his proof of Hörmander's theorem, and that everyone that's seen this proof would know, basically, is that if you look at this property, that that is bad, that the differential is not onto, does not go in all directions. What Malliavin proved is that if you take a white noise, basically you're looking at the LTEs, then almost surely you are not in this situation. Almost surely you do, you can differentiate and go in all directions. Yes. And okay, then I'm going to put myself in a fast framework, so I'm not really using Malliavin's framework exactly, but I mean, these ideas that have been sort of also formulated in some rough paths. Yeah, so I mean, starting with the work of Peter Fritz and Thomas and other people later. So this is based on using somehow the roughness of the driving path. Okay, so from the point of view of the gradient flow, this is not super useful a priori because it just tells you, okay, you don't start on a saddle. Okay, but this is not exactly what we want. We don't want to know where we are at the beginning. We want to know where we are at the end. We want to know that the gradient flow does converge. Okay? So not only do we not start, are we not stuck immediately, which is okay, but this is far from sufficient for what we want. Okay, so basically the goal of this project is to try to look at this question of control of this gradient flow for the control problem, and starting from a stochastic initial condition, and hoping somehow to use the roughness of the initial condition to prove the convergence of the gradient flow. So maybe, yeah, so there's two things. So the question would be to see, okay, does this roughness actually help for the gradient flow to converge? Or at least does it help us to give us some kind of idea of proof that we want to prove that? Okay? And in the rest of the talk, I will give some answers to this, sort of partial. So for now, the results we have we require quite strong assumptions, but we do nevertheless have some results. Okay. Okay, so now let me talk a little bit about why. I think it's sort of a natural enough problem that it would make sense to look at this even without outside motivation. But the way we came to this problem was looking at literature, some of the deep literature on deep learning. So for those of you who don't know me, just let me just say that I am absolutely not a specialist of deep learning. I have never implemented a neural network in my life, but nevertheless, we can find some interesting mathematics there that I think could be somehow related to the thing that we are doing. So okay, so let me describe. It looks like I have some. Okay, because it's. Okay, it doesn't matter. Okay, so very okay. Let me describe quickly the idea. So we have some map which goes from Rn to Rn to simplify, and we don't know it, but we would like to approximate by some other function. And we want to say this expectation. This is an expectation. We know the probability measure. So we have this unknown map y. We want to approximate by a map phi, and we want this to be small. And in practice, of course, we don't know why, but what we do know is like some finite sample. We have some data, which is a finite sample of y. So let's say, for instance, we have a finite number of points xi for which we know the value of y. And so we don't have access to this quantity in general, but what we can try to do is minimize the so-called empirical loss, where we replace this measure by somehow this discrete measure obtained from the data we have. Okay? So we have some phi, we want to find some phi in some class of functions that will minimize this functional. And then, of course, the hope is that if we have a minimizer here, this one is not so far off from zero. Okay, and the specific class of functions that we're looking at here is given by so-called residual neural networks. So neural networks mean you have a certain number of iterations, where at each time the next layer, so xk, depend in some nonlinear way on your previous value, and you have some parameters theta that you choose. Basically, this is the parameterization of phi. You change theta to do whatever you want, and residual means that you have this situation sort of looks like a perturbation of the identity. Okay, and of course, if you see this, it does look. I mean, especially if you add a small delta here, it clearly looks like you are looking at the discretization of an ODE. And of course, this has been observed by people already some time ago, and there's a lot of papers drawing on this connection. So unfortunately, the analysis has been cut here, but yeah, this is quite a big literature drawing on this. Okay, now let me be a little bit more specific. Is that, like I said, what we want to do is start from something that looks like, for instance, a Brownian motion. So we don't want to look at these neural networks as a solution to ODEs, but more like a solution to SD. Okay, and this is, I mean, fewer people have looked at this, but it is also something that has been present in the literature before. I have mentioned a few papers here, so right. So in terms of what we're doing, maybe these ones are the most relevant. So these are some people from the machine learning community, and what they showed is, I mean, okay, is that yeah, if you have your layer where somehow you have the IID Gaussian noise at its terms, then you should take the scaling factor should be 1 over square root of the number of terms, which for us, of course, is I mean, completely obvious, but I mean, they do a lot more, and they are not they do tests and so on in this machine learning context. But yeah, so if you have some kind of thing like this, it's quite natural to see this as a discretization of an edge. And yeah, I mean, I also mentioned quickly this other paper, so it's quite different from what we do, but at least this was the first paper where they had the idea to use some kind of rough path technology in this context. Okay, so now what about the control problem? So now let me specify to the case where we have this linear structure, so linear, I mean, instant, of course. I mean, the whole theta is, I mean, the map theta to x is not linear, but instantaneously, the vector fields, I mean, you have this sort of linear structures that I had in the first section, and then, okay, if you're now thinking about this continuous problem, so completely, I mean, only thinking in the continuous limit, so the problem of minimizing this finite sum here, you can also phrase this in some way which is similar to the problem I described in the first section, except that instead of moving 1 point to 1 point, you want to move each of the xi to the target y. Okay? And you want to do that, I mean, you want the same parameters, the same control to be able to do that. Okay? So, I mean, one way you can check if this has a solution is that, in fact, you can see this, I mean, by increasing the dimension, it's still a problem of, I mean, okay, you have this higher dimensional vector that you want to move to this higher dimensional vector, so it's still something somehow of the first, of the same form of control problem if you increase the dimension. And this thing has been studied by several people in the control community. So in particular, Agrachev and his collaborator. So Scaliotti, he was a student of Agrachev. He was a PhD studies around these kind of questions. And I also want to mention with respect to this controllability question, I think maybe the nicest result in this direction is in this paper by Kukiro, Larsen, and Teichmann, who are more from the stochastic analysis community. And what they showed is that you can find a fixed number of vector fields, which is 5, but not so important, but a finite number of vector fields that you can fix. And then for any number of points, you can actually find a control that goes in these directions to move any number. I mean, you have any number of points that you can move. You can always move by one control that move each of the xi to the y. Okay? So somehow, yeah, you have only d directions, but you can still move an arbitrarily high number of points to one another. Okay, and right, and in this question, I mean, let's say where is the motivation coming from us is that we have these theoretical results on controllability that tell us, okay, in fact, we can really do basically anything we want. We can always find an exact, a solution that actually exactly solve this problem. But the question is, do you actually find this thing when you run your optimization algorithm? So when you have, in practice, you have your neural network, and then you do some form of gradient descent, and you ask yourself, okay, does this actually converge to? Does this actually converge? Okay, to for instance, at least to a 0 or a small value for the empirical loss, and then what can you say about the actual loss and so on? Okay, okay, and of course with let's say the secondary question, but which is sort of relevant to us, is that in what level does the initial condition that you take on your parameters help, and does it help to take them actually stochastic or even somehow irregular, rough? Okay. So basically, this is a motivating question. And I just want to mention this, that there are a number of papers in the machine learning literature that concern this question of convergence of gradient descent. But in most of these papers, and I mean, I would say all that I've seen, but maybe I've missed some, typically they require some condition on the width of the neural network. Okay, and basically they say that the more data you have, the wider your neural network should be, and the width is somehow, I don't know, the dimension in which you move, or you could also, it's also related to the number of parameters per layer that you have. Whereas what we know, for instance, from these control results, is that in fact this is not really necessary. We could have a fixed width, but then we know in the continuous problem, I mean, okay, the width is sort of the number of parameters instantaneous, but if we increase the depth, we will still be in some over-parameterized regime where we have many more parameters and whatever data we need to set. Okay, and somehow this is not so in the gradient descent results, in the convergence results in the machine learning literature. Most of them do not really use the depth. Okay? Even though, okay, we know from the previous results that in the continuous regime we can actually find some control, so it's quite possible that, I mean, so then it's true that also for, if we, by increasing the depth of the neural network, this would help us to, we could find a solution to the control problem. And are these found by the gradient descent or variant of this that people use? Yeah, and okay, so this is the motivating questions. So like I said, in the first in the first part, we already have partial results for this first part, and somehow this is sort of a type model for this one. So clearly, at the moment, we are a bit far from having actual answers to what is happening in deep learning, but it's quite possible that in a few more steps, we can say something that is relevant to at least some regimes of this question. Okay. Okay, so now let me go to the actual setup, actual results. Okay. Right. Okay, so the last line is okay. So yeah, I mean, I think the problem is this slide here. But okay. Okay, so what are we doing? We are in this setting where we have these D directions, which are smooth and which the UML are generating the tangent plate at each point. So we know we have a solution to the control problem, and we do a little bit of a change of variables. So before we had, okay, so before our control was somehow ut, we had ut dt, and we're going to replace this by we're taking the time integral because we want to be in some situation where this is somehow not regular, so that really doesn't make sense pointwise. And in fact, we separate this into two parts, okay, which we call omega and h. And okay, so omega is the initial condition, and this is the only one that's going to be irregular. Okay, and basically here we take a rough path. So if you don't know what a rough path is, I mean, it's just somehow a C alpha path, okay, where the regularity here at this point can be anything. And what we're going to do is then we are going to we're basically doing the same thing as before. So before we had the gradient flow on L2. So this means that at the level of the integrated path, you will do gradient flow on H1. And this is basically what we do. Okay, so this omega is not in H1, but you can still, I mean, if you know a bit Malliavin calculus, it's not surprising, you can still differentiate in the H1 direction, and you can still define a gradient flow in the H1 direction. And basically, this is what we do. Okay, so we're looking at this map. Okay, so now this is at each time. Sorry, at each. Okay, so there's two times. Okay, but basically we're looking at this controlled ODE, and we want to find something here that moves us from x to y. So we look at basically exactly the same thing that I said before. Okay, this map, which is the squared distance to y for the endpoint. And the difference is that somehow now we are always looking at the specific structure of this rough path omega plus something which is more regular, and we're doing the gradient flow on this setting. Okay, so we can differentiate this in H1 directions, and this is what we do. And we have this trajectory, which is with values in H, which means that okay, this one at each point, and this one it moves with H. Okay. Start from 0 and then it moves. Yeah, okay, and right. And yeah, okay, I just want to make the remark that we do this with rough paths. I mean, because of course this is what I know, but also this would be a bit, I mean, probably it could be done using something like Ito calculus, but it would be a bit painful. And one reason, I mean, one clear reason is that this is not a nice SD in the sense that as soon as your gradient flow has started, your H, it's not adapted in any sense because your gradient, I mean, the gradient, of course, I mean, it depends on where you are at the end of the trajectory, so the gradient is dependent on the whole trajectory. So HT is not adapted to the fluctuation of the Brownian motion in any sense. Okay, so it would be a bit painful to do this with something like Ito calculus. Well, with rough paths, it's really basically automatic. We already know from rough paths that we can differentiate in H1. In fact, we can do something more than this. For this talk, let's keep it at H1. It's really automatic to formulate it. Okay. Okay, and then then we ask ourselves the same question as before, which is now does this gradient flow find the zero of the control flow? Okay, let me start with some preliminary results. Okay, so the first thing is doesn't really have anything to do with the gradient flow, but at least I said before that we knew from the classical Chow-Rashevskii theorem that you can always find a smooth path that goes from any point to any other point. And okay, do we also have the same thing here? In the sense that, okay, if we start from a Brownian motion, for instance, we're going to start from something rough, and then we have this somehow this structure that at any point we're always going to have something rough plus something smooth. Okay? And what we can prove by just modifying a little bit the classical argument is that it's true that for any fixed rough path, you can always find a smooth perturbation that does solve the control problem. So you can always find perturb your rough initial condition in some smooth way, so that you get something that does what you. And okay, another thing that is not so hard to prove is that your gradient flow will converge with positive probability. Okay. I mean, it's not super interesting, but you can say, okay, if I start close enough to 0, that is non-degenerate in some sense, then I will converge. And this is, you can say basically any Gaussian process that has full support, this will converge for at least probability non-zero set of initial conditions. Okay. Okay, and so basically these two results, they tell you that at least and you will have the same if you started from something smooth. So you don't lose anything so the fact of starting from a rough path, you do not lose anything. Okay, which is I guess the first thing you would like to know. But of course, what you would like to know is do you actually gain anything? And I mean here the observation there is an observation that is you can use this notion of true roughness. So yeah, so this tells you the following. So okay, the definition is okay, basically you are older in no direction at almost no point, something like this. But I mean, what is the important part is here is that you can find a condition on the path which is satisfied typically by the stochastic processes that you take, which are not C1. And then under this condition, you have this kind of thing where there can be no cancellations in this kind of integration. Okay? So as soon as, okay, I mean, hidden a little bit is that I should say what is the assumption of F5, but let's ignore this. And it tells you that if you have this integral to be 0 identically, then the only way for this to happen is that the integral have to be 0 identically. Right, which of course, if here you, I mean, the interesting thing is that you have more than one, okay, so if you take this smooth path, this would basically never be true. You could always find some cancellations between them. Okay, and so let's say and like I said, if you take a Brownian motion, for instance, it would satisfy this. And then if you perturb this by something like a finite variation path, this will also be true. Okay, this means that in our gradient flow, at any finite time or at any finite distance from the origin, this would hold. Okay, you would always have this property. And in fact, if you know, okay, Okay, let me recall this this formula, because this was the thing I mentioned in the beginning, that what we want is, we don't want to have points where this is different from 0, but somehow this is still orthogonal to all the dimensions that you can get by taking the differential. And in fact, somehow this thing is, there is a sort of a classical iteration using the Lie brackets that tell you that if you have this condition, then you do not have any directions for which this holds. Okay, so for instance, I mean, I guess this is something which is classical in Malliavin calculus for this, but I mean, in rough path, this has a quite nice, simple formulation. I mean, it can be seen, for instance, in the book of Peter and Martin, that if you have a truly rough path in this sense, then basically there is no degenerate. I mean, there is no you are not degenerate in the sense that you have no orthogonal direction to your gradient. Okay. And what this means, for our problem, this means that remember that I said that this was something like this would be. I mean, sorry, something like this when you have non-zero direction where this is 0 would correspond to saddle points for your gradient flow. Okay, and I said that typically they existed, but what this means is now they don't somehow you are, by starting from an irregular initial condition, you have put all the saddle points at infinity. Okay? So somehow they are not completely disappeared, but you have put them at infinity. Okay? And so this is why it's quite nice that we also have this result that, however, you do not have put controls that do the job at infinity. Okay? So you know that you still have, at a finite distance from your initial condition, you still have plenty of controls that will achieve the problem, but all the saddle points are now at infinity. Okay? So this does not tell you that you converge. This is far from a proof, but it's a pretty nice qualitative observation that tells you that, okay, it's a nice indication that maybe roughness would help. Okay? And for instance, you can deduce the following corollary, that basically, once you start from a truly rough path in this sense, that to know that you converge, it's equivalent to know that you stay bounded. Because the bad things are at infinity, so if you know that you stay bounded, you can show that your gradient flow will converge. Okay, so now what is, okay, so again, this is, none of this is a very completely satisfying result, so let me now present the main result of our work, where we actually prove global convergence, actually convergence to a minimum. So we can do this in two cases. So the first one is not very interesting, but it has to be done. This is the first step. Is when we do this elliptic situation where we do have actually all the directions, so where we know that at each point we have enough, the vector fields do span the whole tangent space. So somehow from the point of view of control problem, it's a bit boring because you could just go in straight line from x to y, but still it's not obvious that your gradient flow will actually converge. I mean, now there are no saddle points, but again, it could go to infinity, it's not clear. But we can show then that in this case, I mean, basically no matter what is the initial condition, you converge to a minimizer, I mean, to a zero of your L. And okay, now what is really the main result is that we assume that we do have this bracket generating condition. We have our vector fields plus the Lie brackets cover all directions at each point. And it's nilpotent step 2, which means that if you then go into the third order Lie brackets, they are all 0. So the vector fields Vi plus the Lie brackets Vi Vj generate the tangent direction. So you could be this kind of sub-Riemannian situation where you have many less. I mean, when the dimension of the control is less than the earlier dimension. Okay, but then the third brackets are 0. And then what we can show is that under this assumption, if you start from a Brownian motion, okay, then almost surely for any initial and target points, the gradient flow converges to the minimum. And what is sort of funny, I mean, I will show the proof in the 5 minutes I have left. Yeah, this is in 5 minutes. Yeah. So I will explain the proof and what is a bit. So we do use the irregularity of Brownian motion, and somehow it's really close. So Brownian motion works, but barely. So if we replace it by something slightly more regular, like a fractional Brownian motion with h greater than 1/2, for instance, the proof would not work anymore. We do use the irregularity of Brownian motion, and we really use it in a it's quite critical somehow the Brownian motion. I mean, I don't know if the result is true or not for smoother paths. I would not commit to anything, but at least the proof for sure it does not work. Okay, so maybe let me explain a little bit of the proof. So the major ingredient is to use Łojasiewicz inequality. So let me explain a little bit what this is. So this is a very standard thing in gradient flow, but I mean, if you have not studied gradient flow, maybe you have not seen this before, and I know I have not seen this before we started this project. It's a very, very, very nice argument, I think. So I mean, if you remember one thing from this talk, maybe this should be it. So you assume that you have a function L which is positive and which satisfies this kind of inequality. You have a lower bound on the gradient in terms of L itself. So for instance, a function that is strictly convex would satisfy this, but this is much more general. Okay, and if you have this, then you can show that, okay, L of x, if you draw a gradient flow, L of x converge, but okay, I mean, this we all know, this is just conval, okay, you do conval and you get exponential convergence of L, but more importantly, and also more importantly for us, because remember that I said that for us, basically convergence was the same as staying bounded, so more importantly, you get a bound, some kind of a priori bound that tells you not only does L of x converge, but x converge to a minimizer. And in fact, the proof even does something a bit stronger, which is that the trajectory has finite length. Okay, and the proof is just basically one line that you look at this quantity times square root of, 2 square root of L plus the length of the path of 2 times S. And using this, it's just a one-line computation that this is non-increasing. Okay, which means that the total length here, I mean, if you are positive, the total length is bounded by basically the initial value here. Okay? And in particular, this converges. And so if this converges, this has to converge to a minimizer. Yeah, okay, because, okay, I should say that this, I mean, one thing this implies, for instance, is that if the gradient is 0, then also L is 0. Okay, so this this condition implies that there is no non-minimum critical point. Okay, so this condition is very strong. It's very uncommon for it to be satisfied, and the way this is typically used in practice is this is more where you know that this holds locally, and then the result is if we start close enough to a minimum, then we converge. To typically another minimum, but we converge. But we don't want something like this. We don't want to make any assumptions on starting close enough for minimum. And so we have to use some sort of variant of this that is more adapted to, that is a bit less strong than this. And somehow what you see, the proof, the generalization is sort of clear. And so basically, okay, what we assume, and okay, remember that for us, we can definitely not hope for something like this because, for instance, in this case where we have saddle points, we know that they are at infinity, but they are still there somehow. Okay? They are at infinity. This means that when we go to infinity, you expect the constant here to deteriorate. And this means that what we're looking for is some kind of inequality of this form, but now the constant can depend on the norm of x. And it turns out that basically by just taking the same proof as before and modifying it just a little bit, as long as your constant does not decrease too much, okay, so as long as the interval here is still infinite, then you can basically do the same argument to show that you converge to a zero of your control function. Okay, so here it's hidden, so I will write it, but this means that basically if you have something that decreases like a power of your norm, it should be not faster than 1 over the norm. Okay. So you want something like C of R greater than something like this. And it turns out that this is in fact in both cases that I showed in the theorem, we prove it with exactly this critical exponent. Okay, let me explain. Let me explain the proof because I have not much time left. Let me just explain the proof in the Brownian case. Basically, you are by doing the usual computations, you are reduced to looking at this kind of quantity. Well, omega is your Brownian motion, and h is in this space h1, and you want a lower bound on this, okay? And, okay, for instance, ignore this one, and assume you just have only one. Basically, you're looking at the L2 norm of omega. I mean, you can change the sign of h, it doesn't change you're looking at the L2 norm of omega minus h. Okay? And now remember that omega is irregular, so to have this to be small, you need your path h to be somewhat irregular, and the point here is to quantify this in terms of the h1 norm. And in fact, you can quantify it in this way. Okay? That this L2 norm is greater than some omega dependent constant times 1 over the h1 norm of h. Okay? And this is not, yeah, and really this is sort of, I mean, if you take something other than Brownian motion, you will have a different power. Okay, so really we have somehow we are sort of lucky that the Brownian motion is just exactly the thing that we do. And okay, so for those who know a little bit Bezier spaces and something like Gaussian measures on Bezier spaces, or let's say the path of Brownian motion in Bezier space. So it's you know that if you look at this specific Bezier space where you have an index of variability 1/2 and you take infinity here for this tuning parameter, then it turns out that something a bit strange that happens is that there are some balls which are not covered by the measure for Brownian motion, and somehow this is the same phenomenon. This is basically, I mean, not exactly equivalent, but the same proof gives you. Okay, so this is not very difficult to prove, but it's quite a fine regularity property of Brownian motion, because if you change the index a little bit, you will get something different. Okay, I guess I'm out of time. So okay, just before I stop, just one simulation where we could find one simulation where here you see we do some kind of gradient flow, and we do this for various values of the Hurst parameter for functional Brownian motion, and we do have this nice ordering that the rougher the initial condition, the faster the gradient converge. Okay, and yeah, I think I'm out of time, so I'll stop here. Thank you.